we're going to see a new approach to approximation algorithms, and this is the approach using linear programming. So the idea here is actually pretty simple. We have two different problems that are very similar to each other but have very different difficulties, hardness. And one is linear programming, the other one is integer linear programming. So what is linear programming or LP? Well, you just have a bunch of variables, and your variables you can assume that they can take rational values or maybe even real values. And so you want to minimize or maximize something. So let's say you want to maximize some Cx, where x is the vector of all of your variables and c is another vector. So you want to maximize some linear combination of your variables, and sometimes you can also have a constant at the end, it doesn't really matter, subject to a bunch of other linear constraints, such that, let's say, a1x plus b1 is less than or equal to 0, a2x plus b2 is less than or equal to 0, and so on. And here the bi's are just constants and the ai's are vectors. Okay. So we're considering this in the cases where this x can have any rational solution. So for each one of the variables in the vector x, you can have a rational solution. And in that case, actually, we can solve this problem in polynomial time. Now, I'm not going to go into the algorithms for solving LP because that would take a whole module on its own. But just know that we can solve it in polynomial time, and actually the best algorithm that we have, unsurprisingly, takes n to the power of omega time. So we always see n to the power of omega. But things get much more interesting if our variables cannot get rational or real values, but can instead only take let's say integer values, or maybe integer values from a small set. So that would be called integer linear programming. So instead of LP, we will call it ILP, and the I is for integer. Now, integer linear programming is NP-hard. And it's actually NP-hard even if you limit your solutions to the cases where the variables can only get 0 or 1 as their values. So that's called 0, 1 ILP. And actually proving that it's NP-hard is super easy. So consider, for example, a 3-set instance. Let's say I have something like x1 or x2 or not x3 and some other clause and some other clause. What I can do is that I can just create one variable in my ILP for each one of the Boolean variables in my 3-set instance, right? And then I can say, okay, I have x1, x2 to xn, and all of these have to be integers, and I say that they all have to be between 0 and 1. So this ensures that I always give a value of either 0 or 1 to each one of my variables. So now I can basically treat my variables as Boolean because they are between 0 and 1. And if I want to have something like this, a clause like this, I can just say that x1 plus x2 plus 1 minus x3 is greater than or equal to 1. Okay? So basically, I can use 1 minus x3 in place of the negation of x3, and I can replace the or with just addition, and I can write the same constraint for each one of my clauses. And then if I solve this integer linear program, I have solved my 3-set instance. And so integer linear programming is harder than 3-set, it's NP. And actually, I can even do max 3-set here. Great. So This being said, we now have two different problems based on what kind of variables we have. One is really easy, solvable in polynomial time. The other one is really hard, it's NP-hard. So, given that ILP is NP-hard, I can take any problem in NP and I can reduce it to ILP, right? Of course, I can have many different reductions, but this is the sketch of all the algorithms that we're going to see. So I take my problem P, or actually let's not call it P. I take my problem L, and I reduce my problem to integer linear. Then I say I can't really solve integer linear programming, so let's assume that instead of an ILP instance, this is actually an LP instance. So we call this relaxation. So I relax my ILP to L, which basically means that I ignore the fact that all of my variables have to get integer values. I just say, give me any value. Now, this step, it's not really a sound reduction, right? Because if I get a solution that is not integer, it's not really a solution to my ILP. And it's not like I can convert any solution back to the solution for that. So the next step, step 1, this is step 2. The next step is usually called rounding. So I get a solution for my LP, and in this solution I have fractional answers. Each one of my variables might have a value that is, let's say, instead of exactly 0 or 1, it's something in between. Now I have to figure out a way of rounding the values. And actually this is the hardest step in most of the algorithms that we're going to see. So I have to somehow round the values so that they become integer. But then the problem is, of course, I will not have an optimal solution to my ILP. So the next step is to prove that this is giving me some particular approximation ratio. So prove some approximation ratio. Okay? So this is how all of the algorithms we see today are going to work. But before getting into the actual algorithms, I want to say a few words about this part. So actually, if you have a particular problem, you might have many different ways of encoding it as ILP, right? And not all of them are equal. Some encodings actually end up giving you a better approximation ratio than others. So, which parts are trivial? The only trivial part is this one. But this reduction is not trivial. Even though we know that a reduction exists, we have to find a reduction that actually works well later on for us and gives us an approximation algorithm. So even though finding a reduction is trivial, finding a reduction that works is not trivial. And the rounding part, as I said, is going to be the hardest part. And of course, this is, well, not part of the algorithm design, but you have to analyze it and prove that your rounding actually gives you an approximate solution. Okay, so with this being said, let's actually try to solve some problems now. And you know what problem I'm going to start with. It's always the example that we use for everything in this course, vertex cover. So we take our favorite problem, which was vertex cover. And let's see how I can write vertex cover as an integer linear program. So again, remember, if you don't remember what vertex cover is at this point, you have to drop this course. But vertex cover is that we have a graph G, and I want to choose the smallest possible subset of vertices so that they cover all the edges. Okay? So how do I write this as ILP? Again, what am I choosing? I'm choosing vertices. So for every one of my vertices, I'm choosing whether I'm going to put it in my solution or not. So in a sense, I have one Boolean value for each one of my vertices. So I can just introduce one integer variable for each one of the vertices and say that that integer variable is between 0 and 1. so that it becomes Boolean. So I say that for every vertex V in my graph, I define a variable, I call it x of v, and the intuition is that x of v is supposed to be 1 if v is in the vertex cover, and it's going to be 0 otherwise. Okay? But this is what I want to happen in the end. Right now, the only thing that I know is that I have one variable for each one of my vertices. So how do I actually write constraints that ensure that these variables give me an encoding of a vertex cover? Well, first of all, I know that for every vertex v, the variable corresponding to v has to be between 0 and 1. This is because, of course, I can take only these two values. But what else do I want to say? I want to say that every edge is covered. Okay? So I want to say that for every edge, let's say that the edge was uv, and in my edge set, so one of the two endpoints has to take the value of 1. Or an easier way of writing that is to just say that x of u plus x of v has to be greater than or equal to. This is again the same idea that I had in 3 set. Instead of or, I'm just using sum. Okay, so this is now the set of constraints that I want, but in my ILP I want to also minimize or maximize something. So what is it that I want to minimize? I want to minimize the size of my vertex cover. So I want to minimize. Now, how do I write the size of my vertex cover based on these variables? Well, it's just the sum of all of these variables. So I want to minimize the sum of all xv subject to these constraints. So this whole thing is my ILP. And of course you can see that any solution to this ILP, so any solution to the constraint part, is a vertex cover. And then since I'm minimizing the size, I'm getting the smallest possible vertex cover if I can solve this. Okay. Now, the trivial step. The trivial step is that I drop this I and I just say, let's look at this as an NP. Okay? So what happens now? Basically, instead of just assigning 0 or 1 to each one of my vertices, I'm assigning some number between 0 and 1. Right? And then I'm saying that for every edge, the sum of the two numbers at its two endpoints has to be at least 1. Right? Okay. So let's say I find a solution for this. A solution for this is not necessarily going to give me an optimal vertex cover. Right? So actually, I would probably put this in the example. I've come up with examples where a solution here is awful and not really close to an optimal vertex. Okay. But here's what I want you to see. Do you agree that the optimum solution for the LP is less than or equal to the optimum solution for ILP? And by that I mean this value that we're minimizing, right? So when I'm going from ILP to LP, I'm giving myself more flexibility. I'm saying choose any non-integer value that you like. So any solution to the ILP is also a solution to the LP. So the minimum solution of the LP has to be less than or equal to the minimum solution of the ILP. So whatever result I'm getting here after solving my LP, it's going to be better or smaller than the size of my actual smallest vertex. Okay, but how do I round these numbers? So I have now a graph, and let's just take a very simple graph. Let's say I have 0.3 here, 0.7 here, 0.8 here, and 0.4 here. Okay, I mean this is not even optimal for the LP, but just assume for a second that it's better. Actually, I can do it's 0.7 here as well, so that it's optimal for the LP. Okay, so my LP has given me a solution that looks like this. How do I convert this to a solution where all of my values are either 0 or 1? Well, one very trivial thing would be to say, I just take any value that is non-zero and I turn that into a 1. Right? Would that give me a vertex cover? Yes, because whenever I have an edge, I know that the sum of values on the two sides is at least 1, so there's at least one of these two that is non-zero, so if I take any non-zero value and round it up to 1, I get a vertex cover. But how far is that from my optimal vertex cover? It can be terribly far. Because you can imagine that I can have maybe a complete graph, and, well, that's not good. So maybe I have a lot of values that are really small. So just imagine that I have, okay, maybe something like a star. So let's say I have something like this, right? And let's say I put 0.99 here and some very small epsilon on each one of these. Okay. Now, if I round all of these numbers, and this is like more than 2 times. If I round all of these numbers up to 1, then instead of getting a vertex cover of size 1, which was the optimal, I'm getting a vertex cover of size n minus 1, or n. So, yeah, even though this gives us a vertex cover, it definitely doesn't give us a good approximation. But of course, I don't have to be so stupid in the rounding. I can actually do normal rounding like a normal person, and I can say that I take anything that is at least 1/2, and I increase it up to become 1, and anything that is less than 1/2, I just decrease it to 0. So I round, basically. So why would that work? Well, let's say I have an edge, UV, right? So I know that the value assigned to U plus the value assigned to V are going to be at least 1, right? So at least one of them has to be more than 1/2. So at least one of them will be rounded up and become a 1. So this edge will be covered by my vertex. Okay? But what happens if I do a rounding like this? Well, am I really increasing my answer? Yes. But by how much? So I'm just taking some variables that used to have a value of 1/2 or more, and I'm increasing that value to 1. And I'm decreasing some other variables, but let's forget about the decrease. Let's just take the increases. So I'm increasing each one of my variables, and I'm making it at most double, right? So I'm increasing it from 1/2 to 1. So whatever solution I get, my solution is going to be less than or equal to twice the answer that I originally had for my LP. So twice the optimum of the LP. But the optimum of the LP was less than or equal to the optimum for ILP. So my solution is at most twice the optimum for ILP. And the optimum for ILP was just my minimum vertex cover. So I have a 2 approximation. Okay. So this is the simplest possible example that you will see probably in every approximation algorithms course when it comes to using linear programming. Now, this was not necessarily better than the algorithm that we had before, which didn't use linear programming, but this is another way to get the 2 approximation. Okay. So let's make things a little bit more interesting. And let's go from vertex cover to set cover. Okay. Again, remember that in set cover we have a finite set. Let's call it S. And just to make matters easy, let's say that the elements are 1, 2, 3. Just number them like that. And we also have a bunch of subsets of S. So we have a sequence S1, S2, Sm, and all of these are subsets of this. And our goal is to pick the minimum number of subsets so that they cover all the elements in our set. Okay. Now, I want to model this one again as integer linear programming. Now, again, think about what I'm going to choose. For each one of these subsets, I'm going to choose whether I want to take it in my answer or not. So I can just say that I have a Boolean variable for each one of these subsets. Okay. So let's say I have a Boolean variable xi, and xi is 1 if si is picked in my solution, and it's 0 otherwise. Again, whenever I give definitions like this is just what I have in my mind. This is what I want to obtain. I have to actually write an ILP that guarantees this. Okay, but what is my ILP now? Well, first of all, what is it that I want to minimize? I want to pick as few sets as possible. So I want to minimize the sum of all the xi. Okay, so minimize the sum of xi, where I goes from 1 to 2. Now, what are my constraints? Well, I want the subsets that I pick to cover all of my elements. Right? So how can I write this as a constraint in ILP? I can say I take each one of the elements, and then I write a constraint that says this particular element has to be covered. So I say for every j that is in S, so for every j that is between 1 to n, I write a constraint. Now, what is the constraint? Well, at least one of the subsets that contain j has to be included in my answer. So if I just take the sum of the xi's corresponding to the subsets si that contain x, then that sum should be at least 1. So for every j in S, the sum of xi. Now, how is this I chosen? It's just that si has to contain x, or has to contain j. So I take all the si's that contain j, and I just sum up their variable xi. And this thing has to be greater than or equal to. And of course, as usual, we can also say that every xi has to be between 0 and 1. So this is for every I that is less than 1. So I have n constraints here and m constraints here. And I'm just minimizing this. Okay. So this is my ILP now, and of course, again, this is a valid reduction. Any solution to this ILP is a covering of all the elements using some of the subsets, and then the optimal solution to this ILP is the minimum set. Okay. So now the trivial step, I look at this not as an ILP but as an LP. So let's say I solve this problem as an LP, and I get some optimal solution of the LP. So now the problem is how to do the rounding, how to actually find the solution to the original problem based on the solution of the LP. So my xi's in the ILP were supposed to be either 0 or 1, but now that I've solved the LP, I have found some number between 0 and 1. It's not necessarily 0 or 1, it can be anything in between as well. So I have to come up with some interpretation for that. What does it mean if I say like half of S2 is picked? Does that actually have a meaning? Well, the simplest meaning that I can assign to it is to just interpret these xi values as probabilities, right? Because I know that whatever solution I found would give me a value for each xi that is between 0 and 1. So I can think of that value as some sort of a probability. Okay? So after I solve the LP, here's my rounding algorithm, or algorithm for actually the set cover itself. I say just for each one of the subsets, pick it randomly, but the probability that you pick it would be the corresponding xi. Okay? So I just say pick each si with probability xi. And the decision that I make for each one of my si's is completely independent of the other subsets. Okay? Now, so this is a randomized algorithm now, but we have to analyze a bunch of things. Well, first of all, we have to analyze the probability of success. And for us, success here is when we pick all the elements. Then when we cover all the elements. Okay, so I have to find the probability of success, but also it might be that I'm very unlucky and I pick too many sets here. So I have to also find the bound on the number of sets that I'm expected to take. So what is the expected number of SIs that I take into my set cover? Okay, so let's first do the probability thing, and we have to edit this algorithm to make the probability work. So what is my probability of success? Let's find the probability of failure instead. Let's say I take some element j, and I ask you what is the probability that the element j is not covered. Okay, so what is the probability that j, which is in S, is not covered in my algorithm? And by that I mean I haven't taken any SI that includes j. So here's the thing. I can just look at all the subsets SI that included the item j, and I can just see what is the probability that I don't take any of them. So this whole probability is the multiplication over all the sets SI that include the item j of the probability of not picking SI. Right? Because the only way that j is not covered is if I don't pick any of the SI step. Okay? But this is just, okay, let me write the same thing. J in SI. What is the probability of not picking SI? So I picked each SI with probability xi. So the probability of not picking it is 1 minus xi. Okay. Now we apply our favorite inequality, which we applied in every single one of the algorithms that we were analyzing in the randomized algorithms part. And that's like 1 minus x is less than or equal to e to the power of minus x. So this is less than or equal to j in Si e to the power of minus si. Okay, but I'm just having a product of a bunch of exponential terms. So this is just e to the power of the sum of minus xi, so minus the sum of xi's. And this is, again, for all the sets Si that include J. So I'm over all the Si's that have J. I'm sorry if you can't see this. It's e to the power of this. Okay. Now, where have we seen this sum before? Yes, right here. So we know that this sum is greater than or equal to 1. So e to the power of minus this sum is at most e to the power of minus 1, which is 1 over e. Okay. So great, you see, the fact that I was taking these xi's from the solution of my linear program guaranteed that these sums are always greater than or equal to 1. And that guaranteed to me here, finally, that the probability that each one of my elements is not covered for any fixed element j is at most 1 over e. Okay? Nice. But I want to make this probability even smaller. Right? Because I have n different elements, and my next step is I want to say what is the probability that at least one of these elements is not covered. Right? So for that, I need this probability to go down so that it's less than 1 over n, so that I can multiply it by n. So we've seen this before. Just repeat this whole thing log n times. Or, well, O log n times. You can find the constant on your own. So I just repeat this algorithm enough times so that I can say that the probability that each one of my elements, each j, is not covered is going to be less than or equal to, let's say, 1 over 2n. Okay? So I know how to make the probability less than 1 over e. That's just running that algorithm once. If I repeat the algorithm some constant times log n times, then I can make it so that this probability in the repeated algorithm is at most 1 over 2. Okay, but anyway, this was the analysis for one iteration, so I'm going to erase this. This is now after log n iterations. Okay, but now with this edited algorithm, for every j that is in my set, the probability that j is not covered is at most 1 over 2. So what is the probability that some element is not covered? Well, I can just use union bound, right? I can say I have n elements, and each one of them is not covered with at most this probability. So the probability that there exists some element that is not covered is going to be at most 1 over 2. Great. So now I know that this algorithm will cover all of my elements and will actually give me a set cover with probability more than a half. So this is the probability of the failure of the algorithm, which is less than or equal to the half. So the probability of success is more than or equal to a half. Now I can make this probability again as small as I want. Right? So if I was repeating it here, let's say 5 log n times, I just repeated 10 log n times. And then instead of a half, I can make this probability of failure as small as I want. I can make it as close to 0 as I want. And in any case, I'm going to repeat this whole thing O log n times, because these repetitions, I'm just increasing the number of repetitions by a constant factor. Okay. Great, so I can make sure that I get an algorithm that works with probability 1 minus epsilon for any particular epsilon by just adjusting the number of repetitions. But this algorithm just gives me a set cover. It's not guaranteed to give me an optimal set cover. And if I just wanted a set cover, I could just take everything. So the next question is, how big is the size of the set cover that we're getting? Now, again, here what I can say is that look at the optimal solution of this LP. The optimal solution of the LP is definitely less than or equal to the size of my minimum set cover. Right? Because the ILP was modeling the minimum set cover, and when I went from ILP to LP, I relaxed a lot of constraints. So again, I have more solutions in my LP than I had in my ILP. So the minimum answer of the LP is definitely better or smaller than the minimum answer of the ILP, which was my minimum set cover. Okay. So what is the number of subsets that I'm taking here? Okay, forget the repetitions. What is the number of subsets that I take in every iteration? So I'm going over each one of my subsets and I'm taking it with probability xi. So what is the expected number of subsets that I take? It's just the sum of all xi. So that's actually another nice point here. This thing that we were minimizing here, this is the expected number of subsets that my randomized algorithm will take in each one of its iterations. Okay? But how many subsets am I taking in total? Where I have log n iterations, and in each one of them, I'm taking these many subsets. So my solution, whatever my solution is going to be at most the number of iterations, which was O log n, times this thing, but this was the optimal of my LP. The optimum of my LP. Right? But again, the optimum of my LP was less than or equal to my minimum set cover. So the size of my solution, or actually to be more specific, the expected size of my solution is at most something that is O log n times my optimal answer, which is my minimum. So again, this is giving me an approximation ratio of O log n. And we have seen before how we can get an approximation ratio of O log n without using this whole idea of LP and randomization. But actually, this algorithm usually works better than the previous algorithm in practice. Because in a sense, this idea that these xi's are actually the probability of taking each one of the si's, that's a nice idea and it really works in practice. But in theory, all I can say is that the expected size of my solution is log n times the optimal, and the probability of success can be as close to 1 as I want. So I can just choose the number of repetitions so that I get as close to 1. Okay. Now, one thing that I'm going to tell you is that actually the size of the solution is going to be O log n times optimal with high probability. So here I'm just showing that the expected size is at most log n times optimal. But actually you can show that the size is log n times optimal, at most log n times optimal with high probability. And you have to show that using a Chernoff plot. So we already know how to do that. And this is one of your examples. Okay. Now let's go to a different problem. We talk about a problem that we have not seen before. This is usually called the store location problem or facility location problem. So the markers are dying today. before I tell you what this problem is, I have to define a metric space. So for those of you who have already taken mathematical analysis, you probably know what a metric space is, but the definition is pretty easy. So a metric space is just a set M and a function D. So this set M is the set of points that we have, and the function D gives a distance to every pair of points. Okay, so D is a function that takes 2 points and just gives me some real number. Now, it has to satisfy some constraints, of course, for it to be metric, and the constraints are as follows. So the first constraint is that the distance of everything to itself has to be 0. Okay, so for every x in M, the distance from x to x is 0. The second constraint, which is very trivial, is that the distance from x to y is the same as the distance from y to x. So for every 2 points, x and y, in my metric space, the distance from x to y is the same as the distance from y to x. Okay. The third point is that if the distance between 2 points is 0, those 2 points are the same. Okay? Or in other words, if I take 2 different points, then their distance is going to be more than 0. So for every x that is not equal to y, the distance from x to y is strictly greater than 0. And finally, I want to have the triangle inequality, which says that if I want to go from x to z, and let's say this is my shortest path, if I have some other point y, and I go from x to y and then from y to z, that's not going to make my path any shorter. So in other words, for every x, y, and z that are in my metric space, the distance from x to y plus the distance from y to z is going to be greater than or equal to the distance from x to z. Okay? So whenever we have a bunch of objects and we have a distance function that satisfies these requirements, we say that this is a metric situation. It's a metric distance and it's a metric space. Now, it doesn't have to be any of the distances that you're familiar with, but for example, the Euclidean distance is, of course, giving us a metric space. But if you have, let's say, a graph, and so if M is the set of vertices of a normal graph, undirected graph, and then if you say that the distance between 2 vertices is literally their graph distance, then it again satisfies all of these requirements. Okay. So this is what a metric space is, and now I can actually define my problem. So my problem is, well, let's call it the metric store location problem. So imagine that you're a corporation and you want to open a bunch of stores, or you want to open, I think in the original paper they call it facilities, and you have a bunch of different places where you can open your stores. Make sure I use the same notation here. So let's say that opening a store at, let's say, point I takes some amount of money, and let's call it Fi. So you have n different locations where you can open stores. And at location I, if you want to open a store there, you have to pay Fi units for opening the store. And then let's say that you have a bunch of customers and you want to deliver some, let's say you're Amazon, you want to deliver some goods to the customers, and you know where your customers are. So for every customer J, let's say the shipping cost from a store that is at position I to this customer J is Cij. Okay? And these are all the things that you will get in the input. So in the input of the program, you will get the Fi's and you will get the Cij's. Now, what is your goal? You want to open a subset of the stores and you want to serve all of your customers. But you want to minimize the total cost. So you want to minimize the cost of opening the stores plus the cost of serving all the customers. Okay? So let's write this as an ILP. But before that, so let's just look at the problem. We have to consider two things. We have to first decide at which locations we want to open a store, and then we have to decide an assignment. We have to say which store serves each customer. So each customer has to be assigned to a store. Now this second part, the assignment, is kind of obvious if you have the first part. If you already know which stores you're going to open, then of course you're going to assign each customer to the closest store. Oh, and by the way, the metric part is that these are actually distances. This is like literally the distance from store I to customer J. But again, we don't have more information about this. We just know that these numbers came out of a metric space. We don't know anything more. So our input is just these numbers and these numbers. Okay. So let's write this as an ILP. So what do I have to choose? Well, for every customer, I have to choose which store they have to go to. So maybe I can just have a variable xij that is 1 if customer J goes to store I. Okay? So that's the first type of variable that I'm going to have. Xij is 1 if store I serves customer J. And it's 0. Okay, but this is all I need for the assignment. I have to also choose a subset of my stores. So I say yi is a variable that is 1 if I open store I, and otherwise it's. Okay, so these are my ILP variables. And again, as usual, my ILP variables are actually Booleans. So my ILP starts with saying that all of these variables are between 0 and 1. So I know that xij is between 0 and 1, and this is for every xij, and I know that yi is also between 0 and 1. Okay. So first of all, again, what do I want to minimize? I want to minimize my overall cost. But how can I write my overall cost? So my cost has two components. The first component is for opening the stores, right? And for that, I can just look at every one of the yi's, and if the yi is 1, I have to add the cost of that store. Otherwise, I don't have. So that's just the sum of yi, fi for all of my stores. Okay. The second component is the shipping cost. And, well, that's again very similar. It's the sum of Cij, or actually let me put the variable first. It's xij times cij. Right? So cij is the cost of serving customer j from store I, and xij is just a boolean which tells us whether we're doing that or not. Okay, and this is over, of course, all I and j. Okay. Actually, I can write this sum as two sums, and that's probably better. So I can say this sum over every possible customer j of the sum over every store I of what I had before, xij times cij. Okay, now, why am I doing this? Because I want to have this sum explicitly separated for each one of my customers. Okay, so this is my cost function, which I want to minimize. These are the bounds on my variables. What other constraints do I need? Well, I need to say that every customer is served, right? So how can I say every customer is served? I can say that for every j, for every customer j, I should have at least one of the xij's that is 1, right? So the sum over every possible store I of xij should be greater than or equal to 1. So all this says is that every customer is served. And this is not just one constraint, I have one constraint for each one of my customers. Okay. Is this all, or do I need more? Yeah, so they can only be served from a store that is actually opened. Right, so if I have a store that I did not open, I cannot use it to serve any customers. So how would you write that? Yes. So if xij is 1, that means that store I is actually serving someone. So if xij is 1, then yi should also be 1. Or in other words, xij should be less than or equal to y. Because again, we're only working with 0 and 1 here, so that's all. And this is again for every ing. So now I finally have an ILP that really models my problem. Great. So the next step is the trivial step. We look at this as an LP, and we solve it as an LP. So it gives us a solution, but the solution that it gives us is again not really an integer solution. So it assigns some value between 0 and 1 to each one of our stores. So I have a situation where intuitively a store can be half open, or it can be some fraction open. Okay? And it also assigns, okay, so this was the opening value. It also assigns some value between 0 and 1 to each store and each customer, which is like this customer gets this fraction of its service from this particular store. So each customer can get service from many different stores. But of course, the important point is that the sum of all the services that this customer gets is at least 1. Okay. Great. So this is all we know at this point. But first of all, I want to ask you a very trivial question. In the optimum solution to this LP, is it possible that a customer gets more than 1 unit of service? So is it possible that this sum is strictly more than 1 for a particular customer? Oh, and we're also assuming that these costs are not 0, so no customer is on the same as any of the stores. Okay? So no, because if this sum is strictly more than 1, then I can take one of these xij's and I can decrease it so that this sum becomes 1. And decreasing it does not increase the thing that I want to minimize, my cost. Right? So I can always assume that in my optimal solution, this sum for every customer is exactly 1. Okay? Or in other words, it doesn't matter if I say this is greater than or equal to 1, or if I say it's exactly 1. And I can do the same argument for the ILP case as well. Actually, in the ILP case, it's in this. Okay. So I say this is exactly 1, and I say this is less than or equal to yi. Nice. Now I have a solution. I want to somehow round this solution so that I get an integer solution. Now I can again do the first stupid idea that I had for vertex cover, and I can say I just look at each one of these variables, and if its value is not 0, I just round it up to 1. Okay? That will definitely give me a solution. Of course, it will not give me an optimal solution. It might really give me a terrible cost. Now, why is that? Because it might be that all of these xij's are really small numbers. So my LP doesn't know how to assign these things. It's just optimizing for the LP, of course. So it might be that each customer now has to get service from 1,000 different points and just takes a very tiny amount of service from each of the stores. Okay? And it might be that all of those stores are open only a tiny bit because the store has to only be open more than the service that it gives, right? And then if I round everything up, I'm basically opening all of these stores, which has a huge customer. I don't want to do that. Okay, so that's not a great idea. But what can we do? So, of course, there are two problems here. One is choosing which subset of the stores to open, and the other one is to find an assignment. And in a sense, whenever we solve one of these two problems, the other one is trivial. So if I tell you which subset of the stores is going to be open, you can trivially find the best assignment. Just send every customer to the nearest store. On the other hand, if I give you the assignment, it's obvious which stores you have to open. You have to only open stores that someone has been assigned to. If no one is assigned to a store, you don't open it. So if I can solve any part of this, the other part becomes trivial. Okay. So let's do something really crazy. And let's say that I take each one of my customers. So I take, let's say, customer J. And suppose that the service that was supposed to be given to this customer has been divided between a bunch of stores. Okay? So let's say that J got service from I1, I2, I3. Okay? And of course, I have a bunch of other stores that are not giving service to J in the optimal LP solution. Now, of course, it would be crazy if in my final solution I somehow decide that J has to go to some of these stores. That's really weird. I would expect that my LP gives me some information. And I would expect that wherever J is supposed to go, it has to be one of these stores that were giving it non-zero service before. Okay. So I'm going to just say, what happens if I choose arbitrarily? What happens if I take J, or every customer J, and among all of these stores, I just say, go to one of them arbitrarily. I don't care which one, but just go to one store. Okay? How much worse can my solution get? And actually, I'm not talking about opening stores right now, so let's just focus on this part. How much worse does this part of my cost get if I just send anyone arbitrarily? Okay? Or another way of looking at this is, let me call this sum here big Cj. So this is the cost that I incur for customer J. Right? So I'm saying instead of dividing the service to J between all these different stores, just pick one of them whichever, not probabilistically, just pick one of them arbitrarily and send customer J to that store. Okay, how much worse can it get? Again, the problem is that it might get much worse, right? It might be that some of these stores are really close to customer J, but there might be a store that is very far away, but in the solution to the LP, it's giving maybe a very small fraction of service to this customer. And then I cannot choose that store, because if I choose that store, my overall cost will be much higher. So, okay, I can't just say go anywhere arbitrarily, but what should I do so that I can say this? I have to just get rid of all the stores that are too far away, right? So if all of these stores are roughly at the same distance to the customer, then it doesn't matter. I can say go to any one of them instead of dividing between them. Okay? And this is where we use Markov's inequality. But not in a probabilistic sense. So here's what I want to say. What is CJ? CJ is the cost that I had to pay for customer J in the optimal LP solution. So in the ILP solution, I definitely have to pay more than CJ for customer J. Okay? So here's the thing. I want to take all the distances from J to all of the stores that we're serving J. Okay? And I want to say the fraction of stores that are very far away from J is going to be small. So in other words, and you will see exactly why this is Markov's inequality. So this store, so what is this CJ, by the way? This is also the average distance from J to all the stores that are serving J. But the average is a weighted average, and the weight is like how much of the service to customer J is coming from this store. Okay? So the fraction of stores that serve customer J that are away by, okay, I used K here, I don't want to use K, that are more than K times Cj away from J is at most 1 over K. Okay, so I'm saying this was the average distance from this customer to all the stores that served it. Okay? So just consider all the stores that are very far away. Consider all the stores that have a distance that is more than K times the average distance. What proportion of the service can they give to this customer? Of course, it's at most 1 over K. And the proof is also, again, the same as the proof of Markov's inequality. Because if I have more than this proportion, more than this fraction of stores that are this far away, then my average would be more than Cj, but my average is Cj. Okay. So what does this tell me? Well, let's put K here as a parameter, and let's choose a good value for K at the end of our algorithm. But for now, let's just say that I want to get rid of all the stores that are too far away to this customer. So I say this step is actually called filtering usually. So I filter out all the stores that are too far away. So I say if Cij is the distance from customer J to store I, so if Cij is more than K times this Cj, which was the average distance, then just set that Cij to 0. Oh, sorry, set Xij to 0. So this means that I just look at all of the places that were serving customer J, and I take the average distance, the weighted average distance, and then I say any store that is more than k times the average distance from the customer, I don't want this store to serve this customer. And I set that to 0. But if I do this, then this customer might get less than 1 unit of service. This customer needed 1 unit of service, right? So what else do I have to do? I have to basically multiply the remaining services so that this customer gets its 1 unit of service that it needs, right? So in other words, I have to multiply, I have to scale up all the other xij's that were close so that the nearby stores give more service to this customer so that it gets its 1 unit of service. But how much does this change this part of my cost? Well, I'm getting rid of at most 1/k units of service, right? So in order to make it whole again, I just take all the stores that were close to this customer, and I say consider the xij, which is like the amount of service that this close store was giving to customer J, and I just multiply it by something, right? So that their sum becomes 1. But the thing that I'm multiplying by is at most 1 minus 1/k. I don't know exactly what it is. I have to calculate this in my figuring. But I know that I'm multiplying it by something. Let's call it, I don't know, C. And this C is at most 1 minus 1/k. Okay, which is like, okay, sorry, no. This C is at most 1/1 minus 1/k, right? Which is k over k minus 1. Okay, so I just took some number k, I will pick it later, and I said every store that is more than k times average from the customer that it's serving, I don't want this store to serve that customer anymore. And then I also said that I multiply everything, every remaining service by some number so that every customer gets 1 unit of service. But that multiplication, it's multiplying by something that is at most k over k minus 1. And of course, I have to do the same thing here with the yi's. So how much is this store open? Maybe this store has to be open for more now that it has to serve this customer more. But again, the yi's also get multiplied by at most k over k minus 1. So it's now easy to see that here these yi's are getting multiplied by at most k over k minus 1, and these xij's are also getting multiplied by the same thing. So my whole answer gets multiplied by at most k over k minus 1. So this tells me that after I do the filtering, I still have kind of a constant approximation ratio. But my problem is that I still don't have an integer solution, right? So all I know now is that for each one of the customers, all of the stores that are serving that customer are kind of nearby. They're all close to each other and close to the customer. Right? Because if I had a store that was k times farther than everyone else, then I have already eliminated it. Okay, so what's my next step? My next step is that I'm going to say, suppose I have a bunch of stores that are close to each other. So let's say these are my stores, and they're all kind of very close to each other. Now I know how to find these, like any set of stores that are serving the same customer are supposed to be close to each other. But let's say I have a bunch of stores that are all in the same neighborhood, very close to each other. What would you do if you were like a business person and you wanted to open stores here? If you have a small neighborhood and there are all these different stores in there, well, it makes sense to open only one of them, right? But which one would you open? You would open the one that costs the least, right? So I say consider this group of stores that are in the same neighborhood, and among them, just find the store that has the smallest cost for opening. So the cost for opening was, let's say, F1, F2, whatever. Just find one that has the minimum cost, FB, and open that one. Now, what happens to the customers? Well, the customers were suppose this is a customer and they were getting service from some of these. Just ask this customer to only get service from FB. Right? So this is the basic idea. It's a very simple idea. I want to open only one store in each neighborhood. Okay. But actually, how would we formalize this? So again, remember, this is after I've already done my filtering. Okay? So after I've done my filtering, yes, so this is my algorithm. First, I do my filtering, and then I want to find one of these groups of stores that are close to each other. And I said that the way I can do this is just take one customer and see which stores are serving this customer. But actually, I'm going to take this customer, but I'm going to take the customer that has the smallest cost, the smallest CJ in my NP. And you will see why I'm doing this when you see the analysis. So take customer J with smallest cost. Smallest cost in the LP, not in the smallest CJ. Okay? And then let our group of stores, let it be the set of all stores I, such that Xij is greater than 0. So all the stores that are serving this customer. And then take the store that has the smallest cost of opening, the smallest F among all of these. So let's say I star is the smallest or the cheapest store in G. Okay? Now I want to say close all the other stores in G, and any service that they were supposed to give, ask everyone to just come to this I star. Okay? So close all other stores in G and assign the customers to I star. Okay? And then I just keep repeating this. I just keep repeating this until everyone is assigned and until I have an integer solution. So every time that I find an I star, I say that this I star is open, so y of I star is 1, and everything else here, they're all going to be closed. So when I close the store, I'm setting its y value to 0. Okay, so this definitely gives me the solution to my integer linear programming, but now I have to figure out how bad this solution is. Okay, so first of all, what happens to this part? So this was the shipping cost, right? So I did my filtering. So because I did my filtering, I know that the distance from any J to any one of its stores is going to be at most k times the average distance, right? So, and here I'm assigning each one of these J to a store that is nearby. So if I take I star, yeah, so the customers that were supposed to be served by I star are still served by I star, right? So the cost of serving those customers is going to increase by a factor of at most k over k minus 1. But there were a bunch of other customers that were actually maybe not served by I star before. They were just served by some other store in the same group. So I had this group G of stores that were close to each other, and I had this I star, which was the best store I could open here. But maybe there was a customer that was served by some other store. Let's call that, I don't know, I. Or let's call it I prime actually. And let's say there was a customer J prime that was supposed to be served by I prime. But now what am I doing? I'm saying J prime is also served by I star. Okay? But how does this affect the cost of serving J prime? You see, here is where I want to use my metric. I want to say that I star and I prime are kind of close to each other. So it doesn't matter that instead of going to I prime, it's going to I star. It will still give me a constant approximation ratio. Now, how do I say that? Well, how did I find this group G? I had some customer J who used to go to all of these. Okay? But I had done filtering. So the distance from J to I prime was at most k times the average distance from J to everywhere that serviced it, k times Cj. The distance from J to I star is also at most k times Cj. Okay? The distance from J prime to I prime, okay, again I can say that it's at most k times C of J prime. Okay? So I used to have a distance that was just k times C of J prime at most. Okay? Or, well, yeah, okay. So what was the cost that I was paying for J prime? The cost that I was paying for J prime was C of J prime. What is the cost that I'm paying for it now? It's going all this way. Right? So the cost that I'm paying it for it now is at most k times C of J prime plus 2k times C of J. But this is where this one comes in. So I always took the J that had the smallest Cj. So the total cost that I'm paying for J prime now, so that it gets service from I star, is going to be at most 3k C of J prime. Right? So its cost used to be just C of J prime in the LP, but now it has been multiplied by 3k. So it's now 3k C of J. So this part of my cost is multiplied by at most 3k. Okay? What happens to this part of my cost? So remember that when I did my filtering, I already multiplied this part of my cost by k over k minus 1. So I have that. There's no way to get rid of it. But what else is happening after the filtering? So here's the thing. Again, I'm going to draw the same picture. So I had customer J, and this customer was getting service from every store that was in G. So let's just consider a case with 3 stores, but it works for any number of stores. Okay? So this customer was getting service from these 3. And this customer has to get one level of service. So the sum of service that it was getting from these 3 stores was at least 1. So in other words, x of I1j plus x of I2j plus x of I3j was 1. Or I don't need it to be exactly 1, I just need that it's greater than 1. It's actually exactly 1. Okay, but now what did I do? I choose the one that had the smallest cost, and I said I close the other ones, and I just set this one to be completely open. So this every store has to be open at least as much as the service that it's giving to customer J. So these 3 stores together were open for at least 1. So if I take y of I1 plus y of I2 plus y of I3, this was at least 1. Because this is larger than this is larger than this, and so on. Okay? But what did I do? I closed all of them, and I just opened the one that had the smallest cost. So now this sum has become exactly 1. But what I had in my cost was this sum times the cost of opening that store. But I'm opening the store with the smallest cost. So I'm actually decreasing this cost, if anything. I'm either letting it be the same or I'm decreasing it. Okay. Great, so that's the algorithm. Now, final analysis super fast. What am I doing here? Well, this part of the cost, this part, is getting multiplied by at most 3k. This part of the cost is getting multiplied by at most k minus 1 over k. So what is my approximation ratio? My approximation ratio is the maximum of k over k minus 1, sorry, not k minus 1 over k, but k over k minus 1, and that thing there, 3k. Right, so now I want to choose a value for k so that my approximation ratio is as good as possible. So just set k to be 4/3, and then your approximation ratio would become 4. So this is a 4 approximation.